Welcome to this explainer. Today we are tracing the flow of power in a modern F1 race car, straight from its hybrid heart all the way down to the tarmac. Formula One cars really are incredible engineering marvels, and we're going to break down exactly what makes these machines tick.
To keep us on track, here is our roadmap. We're going to start deep inside with the hybrid V6 powerhouse, move through fuel, cooling, and gears, tackle the aerodynamics, look at the suspension and braking systems, and finally, wrap things up right inside the driver's domain. Part 1. The hybrid V6 powerhouse, the beating heart of the machine.
All right, peeling back the bodywork. Look at this. Right here is the 6-cylinder engine, which, crazy enough, actually acts as the main structural support of the car itself. But let's look at how this beast breathes. To feed it, the split turbocharger draws massive quantities of air in through a duct right above the driver's head. That air gets intensely hot under pressure, so an intercooler tucked inside the side pods rapidly cools it down. From there, split ducting feeds this cooled air into separate intake plenums to balance the pressure, before specialized intake trumpets shoot perfectly tuned air straight into each of the 6 cylinders. It's a beautifully precise high-pressure system.
Now, right between those separated turbo compartments sits a literal game changer, the MGU-H, or motor generator unit heat. You can see it right here. It's a brilliant piece of hybrid tech that actively harnesses the otherwise wasted, red-hot exhaust heat venting from the dual wastegates, and it literally uses that extreme energy to act as an electric generator, constantly charging the car's onboard battery.
So the battery takes all that harvested energy and shoots it over to another unit called the MGU-K, the kinetic unit. Because this thing is geared right to the crankshaft, it instantly unleashes up to 160 extra horsepower. I mean, think about that. That is basically the entire power output of your standard commuter car, just bolted on as a push-button hybrid boost. Absolutely wild.
Moving on to part 2, fuel, cooling, and gears, sustaining and translating all that power.
Since pit stop refueling is completely banned during modern F1 races, the car has to carry everything it needs from the starting line. What you're looking at is a massive, puncture-proof Kevlar bladder hidden perfectly inside the monocoque shell. It holds an incredible 30 to 40 gallons of fuel to last the whole race. And to stop all that heady liquid from violently sloshing around under extreme cornering forces, it's packed with internal baffles and one-way valves. This keeps the weight totally centered and low, preventing the fuel pump from ever starving.
But here is the kicker. Pushing these extreme track speeds comes at a pretty brutal efficiency cost. Even with all that advanced hybrid tech, these engines are only getting around 4 to 6 miles per gallon. It perfectly highlights exactly how much raw, continuous energy is being burned to maintain absolute peak performance.
Now, to keep this engine from literally melting itself down into a puddle, those side pods you see are aggressively grabbing clean air and shoving it through massive radiators dedicated to the engine, the battery, and the oil. Meanwhile, all that meticulously managed power hits an 8-speed aluminum gearbox. It connects to the rear axles with special tripod joints that allow the spinning axles to actually tilt smoothly up and down right in tandem with the rear suspension movement. Which brings us to Section 3, taming wind, aerodynamics, sticking that power straight to the track.
Look at the graphics here. See how the front wing forces high pressure over the top and low pressure underneath? That creates suction, or downforce. But check out the curved edges. Where those different pressure zones meet, you get these violent, spiraling vortices. Normally, vortices just cause drag, which slows the car down, right? But F1 engineers intentionally shape them to act as invisible aerodynamic walls. They literally seal off the turbulent, unpredictable, dirty air thrown off by the front wheels, locking in the clean air that's flowing right under the chassis.
And that clean air under the car is absolutely crucial. Notice the forward tilted rake of the floor here. The super narrow gap between the floor and the track squeezes the air, thinning it out before it shoots up through the upward curving rear diffuser. It turns the entire underside of the car into a massive suction cup. And when a driver needs extra straight line speed to overtake a rival, a hydraulic actuator on the rear wing pops open the DRS, the drag reduction system. This flattens out a section of the wing, temporarily dumping that rear downforce for blistering speed. All right, part 4, suspension and braking systems, controlling the beast. Check out these stark contrast in these designs. The extreme internal conditions of the car totally dictate what goes on outside. Up front, where heat isn't a massive issue, you've got simple flexure joints designed to just bend under load. But look at the rear suspension. It has to be heavily beefed up with robust spherical bearings, purely so it can survive the blistering exhaust temperatures radiating right off the back of the engine. And you won't find everyday coiled springs in here either. To stop body roll, the car uses twisting metal torsion bars. And to manage that critical vertical ride height, which engineers call heave, they use this super clever stack of flexible, cone-shaped washers. Mechanics can just quickly swap these washers in and out to make hyper-precise, track-specific fine adjustments.
Now, stopping this missile is a whole other story. Inside the inner wheel assembly, we have intense carbon-based brake discs covered in thousands of tiny, outward-extending holes just to vent the extreme friction heat. It's all managed by dual master cylinders and an electronic bias screw the driver adjusts on the fly to perfectly balance front and rear pressure. Oh, and remember that MGU-K unit we talked about earlier? A huge chunk of the rear braking force is actually absorbed by it to continually recharge the hybrid battery. Talk about efficiency.
Finally, Section 5, the driver's domain, the human element.
At this point, the driver is basically integrated right into the chassis itself. Look at this setup. They are lying semi-upright inside a custom-molded carbon fiber cocoon, slung almost like a hammock. It is such a tight, rigid fit that they literally have to pull the steering wheel off just to squeeze out. They're locked in by a massive 6-point harness and wrapped in life-saving safety tech like the prominent halo device, the roll hoop to protect from rollovers, and a hands device strapped to their helmet to stop dangerous head movement. And then there's the steering wheel. Just look at the insane density of buttons and dials here. It visually proves just how overwhelmingly busy a driver's hands are while pulling massive Gs at 200 miles per hour. It is a literal mobile command center. You've got manual dials for the hybrid energy recovery system, brake balance, engine maps, and differential locks. You've got the DRS toggle, an instant overtake button, pit limiters, and yeah, even a switch to dispense a drink. And all of this sits right alongside the rear paddles used for the clutch and rapid-fire gear shifting.
So where does this all go next? As you can see, current-wide aerodynamic designs intentionally leave behind a massive, turbulent, dirty wake, which unfortunately prevents thrilling close-quarters overtakes. With massive regulatory changes on the horizon specifically aimed at cleaning up that wake to encourage much closer racing, it brings up a fascinating question. Are we about to witness the absolute end of traditional Formula One aerodynamics as we know it? It's definitely an incredible thought to leave you with as we wrap up this explainer. Thanks for joining me on this deep dive into the engineering marvels of Formula